Now we have natural hazards. Natural hazards are naturally occurring physical phenomena caused either by rapid or slow onset events, which can be geophysical. For example, we have earthquakes, landslides, tsunamis, and volcanic activity. We have hydrological natural hazards, for example, avalanches and floods. We have climatological natural hazards. We have example here, extreme temperatures, drought, and wildfires. For the meteorological natural hazards, we have cyclones and storms or wave surges. And for the biological natural hazards, we have disease epidemics and or insect or animal plagues. So these are the natural hazards. Now we have here some terms to tackle on. First, we have the so-called risk. Okay, risk. It is a situation involving exposure to danger. Then we have vulnerability. If we say vulnerability, this is the quality or state of being exposed to the possibility of being attacked or harmed either physically or emotionally. Next term, we have ground shaking or ground rupture. So the second primary earthquake hazard, ground shaking, is the result of rapid ground acceleration. Then ground shaking can vary over an area as a result of factors such as topography, bedrock type, and the location and orientation of the fault rupture. Next term, we have the tsunamis. A tsunami, so as we all know, here in the Philippines, we haven't experienced this, hopefully not, until forever. So, but then, this tsunami was way back in the Yolanda time. So, some of the reporters mentioned about tsunamis. Such a tsunami is a series of waves caused by earthquakes or undersea volcanic eruption. Out in the depths of the ocean, tsunami waves do not dramatically increase in height. But as the waves travel inland, they build up to higher and higher heights as the depth of the ocean decreases. The speed of tsunami waves depends on ocean depth rather than the distance from the source of the wave. Tsunami waves may travel as fast as jet planes over deep waters, only slowing down when reaching shallow waters. Next, we have the earthquake-induced landslides. If we say earthquake-induced landslide or earthquake shaking, earthquake shaking can cause landsliding on many scales, as some of these examples show. An earthquake can cause a slope to become unstable by the inertial loading it imposes or by causing a loss of strength in the slope materials. Next, we have the so-called liquefaction. This is a process by which water-saturated sediment temporarily loses strength and acts as a fluid, like when you wiggle your toes in the wet sand near the water at the beach. So that is liquefaction. Next, we have subsidence. It is the sinking of the ground because of underground material movement. And it is most often caused by the removal of water, oil, natural gas, or mineral sources out of the ground by pumping, fracking, or mining activities. Subsidence can also be caused by natural events such as earthquakes, soil compaction, glacial isostatic adjustment, erosion, sinkhole formation, and adding water to the fine salts deposited by wind. It's a natural process called as loss deposit. So there are most common human activities that will trigger and haste the occurrence of landslides. First, we have the removal of vegetation. Next, we have interference with or changes to the natural drainage. We have leaking pipes such as water and sewer. Modification of slopes by construction of roads, railways, buildings, subdivisions. We have overloading slopes, mining and quarrying activities, vibration from heavy traffic, blasting during road constructions of nearby mining activities, and excavation of rocks. Next, we have volcanic hazards. If we say volcanic hazards, volcanic eruptions that impact people's lives and well-being. Next, we have lava flows. If we say lava flows, it is an erupting volcano can send molten rock or lava flowing or spewing forth. Even while downslope from vents where lava exterior is no longer red, it is still hot enough to ignite wooden structures. They move slowly and cover small area that they generally pose little threat to human lives. Of course, they are hot, especially from volcanic eruptions. We have the so-called pyroclastic flows and surges. So it is a mixture of hot volcanic ash and steam that pours downslope because it is too dense to rise. Many flows develop when rapidly erupting steam carries a large volume of vent ash in a column that rises high above the volcano. Glowing hot pyroclastic flows can race down the flank of a volcano at a speed from 50 to 200 km per hour, and it's very fast, incinerating everything that's flammable in their path, including forest and people. Now we have here the surge. It is a high-speed ash-rich shock wave that in some cases may race across the ground ahead of a pyroclastic flow. Ash and pumice falls. Volcanic ash is composed of bits of pumice less than 2 mm across, light enough to drift some distance in the wind. Ash erupts into a column that can rise 6 to 20 kilometers in the air. Some ash may linger for several years in the upper atmosphere where it blocks radiation from the sun. Next, we have volcanic weather generated by ash eruptions, which then produces rainfall during eruption. We have volcanic mud flows formed when ash combines with water primarily on stratovolcanoes and pours down their flanks at high speeds with a consistency similar to very wet concrete. It is also called a lahar, that is volcanic mud flows. Next, we have poisonous gases. Even if no eruption occurs, gas-emitted volcanoes can pose hazard to humans, animals, and plants. At depths of more than a few kilometers, gases dissolved in the magma are under tremendous pressure. As the magma rises, the pressure drops, which permits gases to exsolve or come out of solution. Now we have VOG, an acidic volcanic smog that is created by volcanic gases and aerosols.